Hi everyone, welcome to LC Math. Today we'll be talking about the complex exponentiation formula. So we will be considering expressions of the following. A plus bi, some complex number to the c plus di power. We're going to evaluate this by taking e to the log of both sides. This is e to the c plus di natural log of a plus bi. And we know how to evaluate logs of complex numbers by doing the following. E to the c plus di log of square root of a squared plus b squared. So that's the log of the magnitude plus I times the argument, which is inverse tangent b over a. Notice that this only gives you one value, and we know that complex powers are multi-valued expressions, so we'll just be putting plus 2n pi I into this formula later to obtain the multi-valued expression. But for the time being, let's work with it like this. So now we can write this as, well, we want to separate the real and imaginary parts of this. So we see immediately that we have e to the c log square root, blah, blah, blah. Okay. We can just write that immediately as a squared plus b squared to the c over 2 power. Because, okay, we can take the 1/2 out. Yeah, c can go there. Excellent. And we have another real term. The other real term is, let's see, where the i's combine. So we get e to the minus, i's are combining there, e to the minus d tan inverse b over a. And now we need to get the e to the I terms. Well, we get one here. That's just d over 2 log a squared plus b squared. And we get another one from c tan inverse b over a. Excellent. This is the completed formula. Just making sure I got it right. Yep, should be fantastic. So now we can plug in special cases of a, b, c, and d to get any complex number exponentiation that we want. For example, let's just consider the simple example of, well, first of all, this should really be seen as a collection of formula. Usually it's not useful in this form by itself, but it contains all the other formula that you might want to know. For example, a to the power of c plus di can be written as, well, if we let b equals 0, then only a couple parts of the formula are going to be applying. It just will be a to the c, e to the I d log of a. Similarly, if we wanted to consider a plus bi to the c power, say, well, notice c is not an integer. We could always use the binomial expansion, but c is not necessarily an integer here, so that's why this formula is cool. The other parts of the formula are useful. Excellent. And we want to consider one final example. We want to consider the example 1 plus I to the 1 plus I power. This is if we let all the constants be 1 and use the fact that the magnitude of 1 plus I is equal to square root of 2 and the angle, or arg, of 1 plus I is just inverse tangent of 1, which is pi over 4. Well, we can immediately go ahead and write this down as, square root of 2 e to the minus pi over 4 e to the I log square root of 2 plus pi over 4. Excellent examples. I would say in general that the whole formula isn't that useful, with the exception of special cases where the arguments and magnitudes are simple. Otherwise, it looks like a bunch of junk, basically, or things that you can't evaluate. All right, let's do one final example, something probably everyone's already seen before. we'll be considering I to the I now. I don't know how many videos there are about this topic. It's everywhere. You just can't avoid it. Don't worry, I'm not going to spend that long on it. So we want to note that I to the I can be derived from this formula by letting A equals C is equal to 0 and B is equal to D is equal to 1. So the argument of I is pi over 2, of course, since, I is here. This is I. And this is a right angle, right? Good. So we can immediately write down that this is just equal to, if we include the multi-valued extension of it, e to the minus arc of I, e to the I 1/2 log of 1, which is 0, of course, plus 2n pi, yep, sounds good, I. Very important to have the I there since it will cancel and make everything real. Final expression for this is e to the minus pi over 2 plus 2n pi. So we have infinitely many real solutions here. Any integer you put in is going to give you a real solution. First one is e to the minus pi over 2. That's the one that you see on most channels. And yeah, it's cool. It's cool. We have a complex power to a complex power. It's a real number. But everyone's seen this before. Everyone's so sick and tired of seeing this. So let's go ahead and see what we can do about this. That's cool. Well, let's ask some other questions. We want to ask the following question. For which values of k is the following expression a real number? Which values of k is it? Well, let's go ahead and look at the next one. K equals 2, for example. We're going to be computing 2i to the 2i power. So we can just quickly do this. This is actually equal to e to the minus pi e to the I log of 4, which is certainly not real because we have cosine I plus I sine I here. Sorry, cosine log of 4 plus I sine log of 4. Not good, not good. We have an imaginary part, but this gives us a clue as to how we can see which values of k it's real for, which have to set the imaginary part of this equal to 0. All right, let's go ahead and start that. Excellent. And yep, sounds good. So let's begin. Using our formula here, we can compute ik to the ik power to be immediately just applying the formula with a equals c equals 0 and b equals d equals k is e to the minus k pi over 2. That's not important anyways. E to the I k log k. This is important. E to the k pi over 2. Cos k log k plus I sine k log k. And this will be real when the imaginary part vanishes. So this has to be 0 here. So this is real for sine k log k is equal to 0. From elementary trigonometry, this tells us that, just for clarity, k log k has to be equal to n pi for some n an integer. Oh, okay. Well, now we're pretty much stuck because we really don't know how to solve this for k. We really don't know very well. That's okay. We can appeal to a special function. We want to study briefly some elementary properties of the Lambert W function, since we can write our equation in terms of that in a somewhat roundabout way, which is typical for applications of the W. All right, Lambert W function. Definition. it is defined as w of x e to the w of x is equal to x, or of course, same thing as w. I'm going to write it in this form. W of x is equal to x over e to the w of x. Same thing. Definition, it just basically tells you that if you ever have an equation with an unknown function times e to the unknown function with something else on the other side, we can write it in terms of the special function of that, which we can evaluate through numerical methods and so forth. All right. We want to discuss a few important properties of this function. Namely, if you put in x equals 0, then w of 0 e to the w of 0 is equal to 0, which then tells us that w of 0 is equal to 0 itself, since the exponential function is always greater than 0. X is greater than 0 for all x. Fantastic. And now we want to get something close to what we have down here. So we will be considering the following substitution. Oh, before we do that, we're going to note briefly that w of n pi is not proportional to pi for every n. So it's just not. If you compute it numerically, you see that it's not true. I'm not going to prove it here. Okay, we're going to be letting w of x to be the natural log. Sorry, we're using log in this video. Natural log of some other function, v of x. Okay, if we do that, we put log v of x into this formula here. It tells us that v of x log v of x is equal to x. And now we just exponentiate both sides here to show that v of x is equal to e to the w of x, which can also be written as x over, yeah, did I do this right? W of x. Yeah, I really wanted to write this up here. E to the w of x is equal to x over w of x, right? I mean, both things I wrote were true. It just, I wasn't going to use that one in this video. Yep, sounds good. The same thing here. So now we have exactly this form. Unknown function, log of the unknown function equal to some variable. We know that it's solved by e to the w of x. All right, so now we're pretty much done here in terms of the Lambert W. So we know that now we have a family of k indexed by n, and to get the real solutions, we have to take n be greater than 0, since the Lambert W of a negative number is typically not real, is equal to n pi over w n pi, which we can compute numerically. First value, n is equal to 0. Well, that's 1. Since using this, e to the w of 0 is just e to the 0, since w of 0 is 0. And that's 1. Looking at first, then Mathematica tells us that it's equal to, this is actually only approximately for these later values, approximately. We have values like 2.9 and 4.3 and values like 5.5, etc. I mean, even if you just numerically calculate them, you'll see that they aren't a multiple of pi. And fantastic, we have now shown that the only integer such that the original expression is real for is the one that we had to start with. So we can now conclude ik to the ik is real for only for integer 1 only, And then you have the other solutions indicated by the Lambert W. But who would think to plug those into the formula? Nobody would think that. Well, I think this is pretty cool. And it let me learn how to use the Lambert W, which is a great function. It appears everywhere. And if you want to see more about this, I mean, definitely feel free to subscribe. I'm sure I'll include some info about it in the future. And have a fantastic day.